Yeah. There we go. Hi, Siddhant.
Hello.
Oh, and you sound great. You sound great. Okay. So if it's okay, I'm recording. I just wanted to let you know this isn't for a podcast, but I
Okay,
wanted to take
fine.
notes. So
Yeah, sure, no problem. Hi,
yeah,
nice to meet you.
yeah. So I got, in fact, you know what? Let me start with this article. So, and I thank you so much for. I'll just put this up. Thank you so much for sending this to me. This was already published in 2021, right?
Yeah, quite. Time flies.
Yeah. Well, no, it's good to have this to work from, actually. Um,
Yeah, I mean, do you know the writer, Anil? He's kind of popular on scientific magazines. Like,
I do, yeah. I've read
yeah,
several of his stories. Yeah.
yeah, he writes nice, like, nice stuff. Yeah,
Well, so the way that I came into this was I someone recommended that I talk to Dr. Tim Maudlin, I think about 2 years ago. And
right.
we did a podcast. I think the first one was on a different topic, but he mentioned the faster than light communications, and I got really excited about that.
Yeah,
My thought, probably like you, but my thought was, what if we could maneuver the Martian rovers in real time, right? Like instead of having to wait 4 light minutes for, to reach Mars, what if we
yeah,
could like navigate them and get camera feeds in real time? Or like the New Horizons probe that's out past Pluto now. So like when I heard about that idea, I got really excited and I did the interview with him, and I think he listed two or three different ways. One of them was yours. It was the arrival
yeah.
time distribution of photons. And then I believe there's also a
Of
Bohmian.
electrons, actually. I mean, it turned out that the
Okay.
same thing doesn't happen with photons. So just
Oh, okay.
that's a minor thing, but never mind. But go on.
Well, so he mentioned that. He mentioned an idea from Bohmian mechanics also as a second approach to it. And so we did the podcast. I sent it. I mean, I got lots of views on it, but I didn't get a lot of feedback. And so I have been promoting that in my own network, and people scratch their heads and go, well, but the no communication theorem. And it's
Mm.
like, okay, so what they're worried about is causality. But this is just my view. But in my view,
That's
if it's
exactly the what.
instantaneous, it affects the light cone, but not causality. So,
Um, there are many things I thought I should say, so I'll just organize myself for a second. So the first two methods, this arrival time and Bohmian mechanics, they are connected, uh, and also disconnected. I should explain that a little
okay.
better. And that's it, right? You just said two ways of.
I think those were the two, and there may have been
Yeah,
one other. It
right,
was about 3 years ago. I'm
right.
actually doing a write-up as we speak. So this again, the ones that I'm truly like I'm like, this is an important interview, and I have several of those. I do the audio or I do the video, right? I put that up and then I transcribe it. I'm using Chat GPT to clean it up and I'm doing written articles based on that.
That's a
So
lot of work. I congratulate you for putting up
it
all this
is, but some
effort.
ideas are worth it. Some ideas
Yeah,
are
I
worth it.
mean,
So
so I can give you like so we will get to the Martian rover thing. That's very much on the cards, by the way. So I mean, I think Tim said either on your podcast or on another one. Actually, I listen to all his podcasts very much, even though, I kind of talk to him now more frequently than before. But I
good.
really like the clarity, and, he's so good at so many things that I do
Yes.
listen to his podcasts more than once, actually. So just to have some good arguments going into your head frequently. Well, so I think so at some podcasts he said the signature might be small or weak and it shouldn't be uh, sort of leverageable to something like, like controlling a rover. To be honest, that's actually not true. The signature is actually very strong, and that's
Oh,
even more disturbing for, s- I mean, should I say I'm not disturbed by it? I mean, what should I say? I mean, it's an aspect of quantum mechanics that has shown up in different forms in different experiments. As you know, with this Bell test, it's all coming from the fact that you have particles which can exist physically. I mean, at least in Bohmian mechanics, you have actual particles which are. So I don't know how much I should talk about Bohmian mechanics, but maybe we should as we go on if necessary. But as such, the theory literally says that stuff like all this is made up of actual particles which live in this world, but their motions are choreographed by an entity which is not in this world in the sense of like electromagnetic waves, which are in this world, right? You have light here, but this wave function or the quantum state, what Tim likes to call it, sort of does not live in this world in a mathematical sense. Like
yeah.
if I pick a point here and I ask what's the value of that wave function here, there is no answer to that question. In that, so let me not get into what the wave function is, but because this entity is kind of like a different kind of object in physical theory than in earlier theories of physics, it produces phenomena that are in stark contrast to what earlier theories could do and could even said could not happen. So action at a distance, at least in a Bohmian theory, is very explicit because you have the particles which are moving around. There have been equations written down for them. And if you go through these equations and try to analyze what's happening to particles, you see that the separation between the particles is not important for the equation. I mean, to give an example, in Newton's laws of gravity, you know that once they're sufficiently far away, the force of gravity acting on one due to the other is really small. So, it's called an inverse square law, right? So it drops very quickly with separation. So after some point, you can just ignore the distant stars or something if you want to talk about the gravitational forces. That is something you couldn't do in Bohmian mechanics. Let me even make it a little more precise in the sense that the theory allows for this, but this is not the norm. It's a bit of an exception. You have to arrange matters to see that action at a distance, because otherwise you
Yeah.
would see it every time. So that is also important to get across because people are always imagining the extreme, which is part of the theory does allow for this extreme correlation between particles. Like, this Bell tests, the way they are understood in a Bohmian theory are with the help of this feature of the dynamics that particles can be
So
very
what?
far.
Yeah. So
Yeah,
what you're saying is people take it to the extreme and say, why don't you see the entire universe? What you're saying is you
yeah, yeah.
have to do the entanglement. And
Exactly.
so,
You need this, and you need yeah, even this so-called maximally entangled states, as they say in quantum information language, to produce this phenomena. And that's allowed by the theory. So it's definitely
well,
a possibility.
okay, if I and I'm gonna I want to lay this out for you, right? Partly, thank God I'm recording notes on this because otherwise I'd be in trouble. So
No
I'm
problem.
trying to kind of remember from what I was writing the other day and from um okay, so I'm here on Earth and I want to communicate in real time with the rover on Mars, right?
Right.
And it's got and so how do I get the entangled particles from here to the rover? the thing is, okay,
Like one way to do it is the moment you launch the rover, you can put one of the particles of the pair in a some box, let's say in the
okay,
rover, and keep one with you. And then the rover can go, of course, the rover has to physically travel till Mars.
yeah.
But then what you asked me is if I were to now give directions to the rover mid-flight to change some operation, like change its direction or something, that will also take time. As you said, if I send light from here, it takes 4 minutes, or you said 8 minutes, or something like
So
that.
so there is a
That won't
delay either way,
that
right?
won't happen with the particle. So that's the difference.
Now,
So
are the particles used like so in a traditional sense, when you measure a particle, it's used up, right? So I would, if I'm using electrons, I would have to create a million electron pairs here
yeah,
and a
you will
million
have to
there.
have a sufficient number of copies. Because in a single pair, as you yourself said, it gets destroyed because if normally to transmit any information in this communication protocols, you do a measurement. And
Okay.
also the receiver does a measurement, and the measurement outcomes are doing the job of encoding and reading, basically.
But if it, I have heard that there are a way to do weak measurements that doesn't destroy entanglement.
That's correct. That's correct.
So
And I haven't thought about the weak measurement aspects of this particular protocol.
I mean, so the traditional model, and again, my brain is fuzzy. I'm trying to kind of think back. In
It's
the
okay.
traditional model, I would have, okay, I create an entangled particle pair. I send one there. I have one here. These entangled particles basically, um, I can send a signal, but in order to decode that signal, I have to do a measurement which
Yeah.
breaks the pair. And so it's used. So it's used up. But
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 you do
in
see the outcome of the experiment, so that's certainly something you get. But you have to
yeah,
repeat.
and in the traditional
Right.
model,
So you are right that
since we're measuring the polarization in the traditional model, um, you have to check that against the original, which now even that being said, that still can go twice the speed of light to me.
yeah, I mean, in theory, it's
So,
instantaneous.
well, it's an instantaneous, yeah, the change happens instantaneously, but the no communication theorem was saying, information can't travel faster than the speed of light, right? Um, but that would be normally you would have a round trip. If you only have a one-way trip, that's twice
Oh,
the
I
speed of
see.
light.
Oh, I see. That's what you're now referring to. Like
But yeah,
we only know the two-way speed of light, that stuff.
but in your model, what you're saying is um you can do changes to the particle that aren't based on polarization, and you can check the arrival time of those changes, and that's instantaneous.
Yeah. I mean, I should say more actually. So this is where the no
Okay.
communication theorem comes in. The idea is, I mean, the basic scheme of the experiment is the same in all these no communication protocols. You share a pair of particle, uh, and between two guys in two different labs, which are supposed to be space-like separated, meaning, light would take very long to go from one to the other, and both of them can do whatever they want with their particles. So in principle, they're going to do measurements. I mean, that's how the discussion starts. Now, this is where, people like John Bell have been very explicit in saying, well, if even if you did prove a theorem about no communication based on measurement as the key thing to be done here, why is that a forbidding theorem for whatever you could do physically,
Yeah.
right? You could. So he then goes on, like he analyzes a situation where you could do something different, like change the Hamiltonian, which is not a measurement, but whatever. So there is already some amount of care that needs to be taken when you want to even decide what counts as a signal, like what you can do with your particles. And that's a discussion one could get into, but let me come back to the no communication situation. So what they do is they have a pair of particles shared between, let's say, Alice and Bob as usual. I like to call them Sheldon and Penny now. I'm got really bored of Alice and Bob. But never mind. So one of them is a signaler and the other one is a receiver. And and let's say the simplest situation is a signaler just wants to communicate a one and a zero. Now, before even we begin setting up the protocol, what is clear is if they have only one pair of particle and they do measurements on either ends, there's nothing anybody is going to learn from it because the outcomes are random, no matter what they choose, right? So already the first piece of nuance here is you need more than one particle, and you need a sequence of particles to do these experiments, like one after the other. But the
Yeah.
idea is let's say you do 5 runs of the experiment, all set up in the same way. I mean, you have to understand this is a very idealized discussion and it already gets pretty wacky very soon. So I can imagine there are challenges to a practical implementation. But the no communication theorem guarantees that even if you repeat these experiments with identically prepared pairs of particles and doing identical stuff on either end, after no number of experimental runs, you could say what Alice is doing.
Yeah. Yeah.
So this is the thing, they express it by saying the density matrices are the same. I don't know if you like this kind of presentation of this theorem, but that's a way some people like to present it that way. So what is different? So it's a theorem, and I think the correct way to see it in the light of what we are going to discuss, and I think people agree with me on this, is that it's more of a compatibility argument. Just a moment. Sorry. So it says that insofar as the quantum mechanical recipe for the outcomes of experiments done on individual particles is what it is, like what is written in the books, based on, what von Neumann wrote in his book in 1935, as long as that scheme is valid, you cannot communicate even with multiple pairs of particles by doing experiments because the random outcomes is sort of random in a way which doesn't even allow you to see any pattern, let me put it loosely that way, right? So if you want, I can even make it a little more precise. Let's say Alice wants to send a 0 and a 1. And if
Okay.
she wants to send a 0, she measures spin x of her particle. So she sets up a magnet in the x direction and whatever. Of course, she will get a random outcome because the particle can go, in the spin measurements, it can go up or down, and up counts as spin up measurement, spin down measurement. But she can measure in different directions, and in any direction, there are two ways to go. Like maybe you tell me if it makes sense. So if this is a spin z measurement, the particle goes and it can go up and down. And if this is spin x measurement, it can go both ways. Right? There are two directions in any along any axis. So the specific outcome she will get is random. That's fine. But she can always choose which direction, or as people say, which basis she wants to choose to. Sorry, I'm saying too much. So she can decide to measure the spin in a particular direction depending on what she wants to transmit. So, and of course, the Bob's particle is available with Bob and he can do whatever measurement he wants. Now let's do the following experiment. Let's say they share 100 pairs of particles. And in all these 100 pairs, Alice does a spin X measurement, like all of them. So that means she was always wanting to send the same value of information or bit, if you like. And Bob can do whatever he wants. He can measure along spin x, he can measure along spin y, he can do any other measurement with his particle, let's say a quantum mechanically sanctioned measurement, and he gets random outcomes as well, right? Now keep this on the side. Take another pair of 100 particles in which Alice does like spin z measurements, which she would do if she wants to communicate a zero, let's say. And then Bob can do whatever, and every time Alice measures, Bob can do whatever he wants with his particle. And he also gets a bunch of 100 random outcomes for whatever
Yeah.
experiment he chooses to do. Now, quantum theory says that the random numbers you got in the first set of experiments and the random numbers you get on the second set of experiment have exactly the same probability distribution. So if you make a histogram on a computer, write them on an Excel sheet, I mean, if you do sufficiently many experiments, they will be the same histogram. Now, what does this have to do with faster than light signaling? It just says that even if you were doing it in real time, one after the other, and not parallelly, even after 100 runs of the experiment, even because individual runs are random outcomes, you can never say what Alice did, right? But if you were to plot the histograms in tandem, like in runtime, in real time, if you're plotting the histogram, you would still not be able to say whether she was doing a spin X measurement on all her particles or a spin Z measurement. So encoding and decoding information by doing quantum measurements is not even statistically feasible in so long as the statistics are compatible with the standard quantum mechanical predictions.
Yeah.
I guess I just wanted to clarify that that's the content of the no communication theorem. And actually, if you look at the derivation, it doesn't even care about space-like separate. It's literally no communication theorem. It says even if you are not space-like separated, you will not be able to figure out. Because in the proof of the theorem, nothing enters as to who is separated by how far and whether light is involved or not. So that's also an interesting observation that
So
it's
then how does your model work around that? Because you're talking again, this is a rival time distribution, which I interpreted to be kind of like Morse code. So instead of doing like a measurement, I kind of envisioned it like you're wiggling this particle and this one wiggles, and you can do
yeah.
like a weak measurement, right? And so they remain entangled. And I know I'm mixing two things there because weak
No.
measurements
We
versus
don't have to. We can do regular measurement.
okay,
Uh, and we can, so let's repeat this same scheme, and let's allow Alice to do her spin measurement. She will always, if she wants to send a 1, she measures spin X. If she wants to send a 0, she measures spin Z, let's say. Now the question is, we never talked about what Bob can do in the previous discussion. We just said he does something that is quantum mechanically legit and gets some random outcomes. But now I'm saying Bob should measure not any particular quantum observable from the textbooks and so on, but he should measure the arrival time of his particle. That means he should have a setup in which the particle was, his member of the entangled pair goes towards the screen, and then the screen clicks like in a double slit experiment, and there's a clock, and he sees the duration between you know so let's say, to make it even more realistic, let's say Bob traps his particle in a box. First of all, they have each one particle, and Bob can just trap the particle in his box. That's allowed. That will not destroy the entanglement. And what he can do is his experiment. Now I'm becoming more explicit about what Bob should do. And that's where the loophole is to the no communication theorem. And I'll say it explicitly. So what Bob should do is his particle should be trapped initially, let's say. And then his experiment should involve releasing the trap whenever he wants to, and then allowing the particle to move towards the screen, like a scintillation screen. And this has to be in, there are many implementations of this, but the one that the article was about is for electrons and spin and so on. So
okay.
but we can get into that about which particle it needs to be and so on. But the basic protocol is as follows. His particle has to be in a trap, let's say. Then he releases this particle. This is Bob's experiment. And the particle goes and clicks. The detector will click after some time, like in a double slit experiment. And all Bob needs to do is to record the time between the releasing of his plunger, let's say, and the click, the sound of the click, like what happens on the real lab, right? Two events, and you measure the duration or the transit time between these. Now, the thing is, if now let's say he has 100 pairs of particles, like before, Alice always does spin X measurement, and Bob does arrival time measurements at his end. So I have now explicitly told you what Bob should do, and he will again get random arrival times because sometimes his particle will arrive at the screen. I'm just using classical language. Some people don't like it, but nobody denies that you will see a click on the screen. So you
Yeah.
will see a click a little later, and this detection time is going to change randomly. It's not predictable like all other quantum outcomes of experiments. And therefore you have a list of random numbers for all these 100 pairs of particles, and you have a histogram. Of course, Bob has a histogram of arrival times now, or transit times, if you like. And then we can do the same experiment where Alice is now only doing spin Z measurements, right? And Bob has another set of random numbers with another histogram in this case. No communication theorem says in the previous instances that these two histograms that Bob will get in these two cases should be one and the same. And therefore, he can never have predicted whether Alice was doing spin X measurement or spin Z measurement. That's
Mm.
basically the framing of the no communication theorem. Now, what I am saying, well, I as in what we calculated and found, I mean, nobody put it in by hand, that these histograms that Bob will get if he were to do arrival time measurements instead of the regular quantum measurements like spin, position, momentum, all that, will not give you same histogram. They will be totally different histograms. So that means, let's say for the first, I mean, Alice and Bob can agree on the protocol, right? Like Alice can send, every time she wants to send a one, she can do the measurement of transmitting a one for 100 times on her particle. And for the next 100 particles, she can do, like if you want to send a Morse code, for example, 1010, like let's say. So they have to agree on a certain fidelity because single runs, if she does a measurement, then nobody will learn anything. So she has to keep a window over which she's
Okay.
sending the same bit. And quantum mechanics says if the window is long enough, statistically, you will not be able to say whether it's a one or a zero because the randomness is the same whether Alice is sending 100 ones or 100 zeros. But if Bob were to do arrival time measurements instead of, um, as I said, any other measurements with his particle, he will see differences whether Alice was trying to send a one or a zero. And this will happen at space-like separation. So this is important, right? I mean, and then the question is, what has changed? Why is the no communication theorem not coming in your way in some way? The reason for that is the property called arrival time has been forever since quantum theory has been in place a huge problem. The theory does not have a natural way to predict the statistics of arrival time, just even in a single particle experiment when you are not doing this fantastical entanglement and stuff. So there, the discussion naturally leads into sort of what has happened in the.
So so it's a
Yeah.
loophole. This is a
It,
loophole
this
in
is the
quantum
loophole.
theory.
Yeah. Uh, this is debatable still because right now there are many. So this is something that might also be nice. And this, what I'm going to say now, also raises the discussion outside a very particularly Bohmian discussion. Let me put it this way. So there are now, at the moment, many proposals for how to predict the arrival time of a particle. In short, physicists are trying to fix this long-standing open end of the theory. And it's unfortunately very scandalous because it's a very simple experiment as we describe it as we speak. And it's being done regularly in the lab for reasons that I can get into because people measure arrival time to measure some other quantities using it. Uh, for example, in
So
CERN.
this is something that could be tested then. You could
Oh,
test,
yes.
you could, oh.
Sure, immediately. Like, yeah, I'm
Now,
really not
is
sure.
there a way to test on Earth? Because I know, right, because the
Yeah.
distances are so small. Is there a way to
So,
test on Earth whether it's FTL transmission, whether it's instantaneous?
um, even before you would do the two particle thing, I would suggest you should just measure the one particle arrival times in certain states for the Bob particle. So just first figure out what are the one particle statistics. And if that violates this what's called the parallelogram law, it's an indirect way
Okay.
of, then that's enough to tell you that if you entangle it and if quantum mechanics does not change now because you have two particles in play, which we don't think so, because all these Bell tests show that the regular assignment of wave functions to two particles and all are correct. And if you already verify at the single particle level the statistics for different sets of wave functions, which Bob should get, that should already put you in a very strong position to suspect signaling in the actual implementation. Then the
Yeah.
question is, you ask, if I now put the two guys in two different rooms and then they are sending signals, it's actually faster than light. Well, I think you can test that. You can as soon as Alice sends, one has to set it up a little carefully, I think, but I'm roughly suggesting like, she can send a signal of light along with doing her measurement. And, she can see if Bob already knows what she did before light reaches a mirror there or a detector at Bob's end. That can be done in the lab.
Yeah. That is just the idea. This idea is so powerful.
Yeah.
This could quite literally open up the solar system for robotics. I
Yeah,
mean,
I mean, you could see so much further, right?
yeah, yeah.
Maybe the
Um,
ninth planet, as some people want to see.
Well, yeah, there are so many potential applications for this. That was what got me excited about it, you know. But the rovers on Mars was, for me, that was the one where I was like, okay, that is a real, honest to God, practical implementation, right? Where, you know, now, so the downside to something like that would be with strong measurements, again, you have to have this exhaustible supply of particles.
Okay, that's the
So,
problem.
yeah, there
But
would have to be
I
some
see
way to
that
do.
more of a technological challenge at this point.
And
Can you?
quantum computing has that issue. Quantum computing, right?
Yeah.
Where the states don't stay, they decay over time.
I mean, that also explains why you don't see this so easily, right? You have to think very hard or in very unusual circumstances. I mean, to be honest, the physics is not like fantastical. Like you're just measuring arrival time, which makes sense to, let's say, your grandmother. But then the beauty of the situation is it's a very long-lasting problem in quantum theory. And all these theorems, there's no communication and so on, they go so abstract and so general, they lose out on these very fine details on, oh, that particular experiment is not part of this framework. So if I prove something within this framework, I should be really worried what happens if somebody
Okay,
conjures this
so
thing.
that is another point that is worth stressing is this experiment is not part of the no communications theorem framework.
Yeah, not in the standard version. Now there is of course, a controversy. So I'm actually in all the discussions sort of suggesting or embracing the view that the statistics that you do get in the Bohr band by arrival time measurements is sort of not compatible with what regular quantum statistics looks like, which is what the no communication theorem sort of utilizes to get its result. And
Okay.
why am I saying that? I mean, it's very hard to, I think, prove that you will, because as I said, there is no quantum prediction for arrival time. What we do have at the moment are many proposals for how to do the prediction. And let me remind you that it's not a very easy quantity to predict. It has a lot of constraints. I mean, not just any quantity is an arrival time of a particle. It should look reasonable, and it has many constraints. Like, if you delay the experiment, your data
Now,
should.
if it's okay to ask, you mentioned there are many proposals, right? Um, do all of those support the no communications theorem, or is it a mixture?
That's where I was heading. So,
Okay.
the question was, why am I more convinced or pro signaling, if you would like? The answer is actually the work that I did was based on Bohmian mechanics, and that's a very famous proposal for doing arrival time calculations, and people used it all along before I came. But in the setup that I designed for with my former advisor Detlef, we looked at it that predicted the statistics. And then the question could be, well, maybe some other theory does not lead to this signaling like statistics and you're fine. And that of course was fair point. And we looked at actually all these proposals. Maybe in the article, maybe Anil even mentions that we have been looking into, I mean, at the moment there are probably 20 odd proposals. And there are hardly two, I think, which will not allow for signaling in this setup, one that I just described, like with two particles. But the problem is those two proposals do not even give you the correct predictions for some adjacent experiments, which we know what the correct answers are. So that's another issue that if you are driven by the idea to make a proposal which does not allow for signaling, you better be sure that it is at least empirically adequate. It makes the correct predictions in certain known circumstances. So the ones which had the chance not to, at least not to let signaling happen in this form, do not agree with experiment in certain scattering cases. And so there are some papers we have written about that. So at the moment, the others, which are seem to be reasonable, they all predict signaling.
Okay.
It's amazing, isn't it?
Yeah, yeah. No, this is exciting. This is exciting. So, in terms of now, so would you be open? You've probably seen my channel, right? So it's very similar to this, but I use Riverside, which is just a Google Chrome based
I
recording
see.
system. Um, would you be open to doing an interview on
Yeah,
on
sure.
like? Okay,
I heard that. I mean, did Tim mention this guy called Will Cavendish? He's like,
He did, and Will is apparently he is working on several different ideas, but he does not want to speak in public until he publishes something. He's working on a paper. So
oh, I mean, technically, we also, I mean, okay. I mean, he is a guy who independently discovered this as well. So it's a bit weird if he, okay.
I think it was related to his paper. I think he didn't want to. I think he was concerned about having the paper accepted and published, and he wanted to get it through the peer review without any controversy. So I think that is kind of
Well, I mean,
his
to be honest,
concern.
I said the same to Tim that, if, I mean, Tim Maudlin, that, if you now make me speak about these things in public, it's only going to get worse because all our grant applications are very tough to get through. And it's a lot of hard work, actually, because these experiments are very difficult to analyze if you look at some of the calculations. And anything that goes into exciting territory that physicists don't like just makes it really worse. I mean, I'm saying this
Well,
after.
to me, it seems like um, it seems like there are always different ways to frame things, and again, this is maybe I should make this as a note to myself, but when you talk about superluminal particle communication or superluminal communications, right? That it violates the no communications theorem or it goes outside of it, that does make scientists nervous. But if you frame this argument in terms of helping to validate various proposals for arrival times, that seems like something that might be
Exactly.
embraced
And
by.
and I thought Will should be interested to come along because he makes this point quite exactly in the way you did. Would have been nice to have him because, he should get
Well, and
credit
he
for
he
all
may,
this.
yeah, he may, I would give him a little time to kind of warm up to the idea. I
Okay.
think a lot of times it's uncertain territory, right? And so that
Yeah,
makes
it,
people
it's
nervous.
making
But
it difficult because some of the experimenters we want to work with, they really got very upset about it. And as such, it's actually not a very deep thing that we are saying because it's very clear that what's if you understand the no communication theorem, especially what assumptions it makes, it's not a big bit of a theorem, honestly. It's even taught to be
yeah,
nowadays. Quantum info, people learn it without even not knowing what a Schrödinger equation is. So it's kind of based on very algebraic considerations. It's not really based on solving some very difficult equations like Schrödinger's equation, right? So it's not really a consequence of quantum mechanics which follows after a lot of work. It follows from the structural material there. And
well,
and
and
easy to see.
the thing that troubles me with it is from the reading that I've done, it seems like a bolt on, right? Like, so in quantum mechanics, they arrived at this idea and they didn't want to upset the relativity physicists. And so it was like, okay, let's just bolt this on here. Yep, So yeah, you can send information faster than speed of light, but oh, you can't measure it faster than speed of light. So we're saving physics. And I'm like,
Yeah,
that
that really is very unsettling, I have to say. And
yeah, it reminds me of, it's like you have a pothole in the road and you don't know what to do with it, so you fill it with dirt. And if you leave it there long enough, it'll look like it's part of the road, but it's not. So
that's a good analogy. Tim is very upset about it. Like he keeps saying, if the correct conclusion of the violations of Bell inequalities is, and which I agree with, is that you have action at a distance. I mean, if that's all you need to explain these many experiments by now, I mean, the next question is why can't you use it or control it in some way to sort of communicate or transmit information? I mean, so okay, this I'll say afterwards about causality violation and stuff like that. That's added thing. There are many layers of confusion here, actually, unfortunately.
there
So
are.
yeah,
Yeah.
and so there's a natural question you should ask here. Why can't you control it? And people are like, oh, if we signal faster than light, yeah, we can, kill your
Well, to
grandfather and all
me,
that.
to me it seems like a misconception, right? But that's because and this will upset a whole different group of physicists. I believe that there's an absolute frame of reference. I believe
Yeah,
that the
I
quantum
also.
foam, right? That's an absolute third frame of reference. And and you can call it what you like. Some people have called it aether or quantum foam or time space continuum, right? You could make all of these different names for it, but this goes back to everything that I've read and all the physicists I've worked with is if everything is absolutely always relative, then you run into some unsolvable issues in physics. So there really needs to be a third frame of reference of some kind. And
Mm,
and so my take on quantum signaling is it is not happening reverse time. It may be faster than the light cone, right? So if you have Alice and Bob, if she sends a photon from Alice to Bob, you're going to have this light cone that goes out and it goes out at a certain speed. And the quantum event happens instantaneously, right? And
mm.
so I think the concern was, well, if everything is relative, that light cone represents current time, but it doesn't. It's a light cone representing a causal event. And so I think all that this experiment is saying is if these particles are entangled, then you can have instantaneous communication. But that, for me, in no way violates causality.
Yeah, for
So
me neither, but perhaps for slightly different reasons. I mean, also not that I have I mean, I have to be honest, I haven't thought really deep about this because there's so many things to do around here to fix
yeah,
all the steps along the way, and one only has a finite time for really figuring out the rest of physics, right? So, one thing that people worry about is can matter be accelerated to speeds faster than light in this? I mean, is some of that here happening here? The answer to that is no, as far as I know. Because in Bohmian theories, which are relativistic, well, there is a lot of, they're not very definitive because people have put up different candidate theories, and I haven't been really working with them either. Although did a relativistic treatment of that particular experiment, which is covered in that article, but that's a one particle experiment. Well, let's forget. The answer is there is no indication that as such particles are traveling faster than light. So the
yeah.
Bob particle, the Alice particle are moving slower than light, but the
And
motion there is correlated in a way that is not mediated by fields of that we are used to, like electromagnetic fields or gravitational fields. So there is a faster than light effect, but it is not happening by making particles travel faster than light, which is
yes, it's
important to think.
information. And I think
Yeah, if
that
you like
for
to
for
use
me,
that word, yeah.
I think that is because we are in the information and computing age, right? And
Yeah.
so I view information is a meta value. It is not a physical value. It is like a structural value. But when
Hmm.
you think about it, every particle in the universe contains information about different events. So information is a very relative term, and
Right, and that certainly
so
upsets
it's
the
you
modeling,
know
right?
well, I mean, like, I have read that a shadow can travel faster than light.
Hmm.
A shadow is information, right? If you have the shadow from a sun and a star, it can sweep through a solar system faster than light. And in theory, if you were looking from a third perspective, you could see it moving. In theory, yes. Now, the actual photons that make it are at the speed of light, right? That I know that's not the best example,
Yeah,
but the
one
idea
might
is
have
that
to model this
information,
more carefully. Like, you have to
yeah,
define the boundary of the shadow in terms of the waves and so on. It's a little
my
tricky.
my thought is that information is a structure and it's a useful structure, right? And because again, everything like every well, like with a Feynman diagram, right? And every time you have a particle information, it exchanges information about that past interaction and all past interactions. So, so my view of things is that information is a meta value that comes down to utility of that information, right? So
Mhm.
it's a very arbitrary meta thing. It is not a physical thing, right? Like we're going to send information. It doesn't have mass, it doesn't have energy. It is just structure of something else. That's just my philosophical thought. But-
So you seem to have given quite some thought into information and how it embeds in the
Well,
physics
one
that you
of
have
the
access to.
Yeah, well, one of the things that I've tried to approach it from kind of a philosophical level, and what I found is we express things. I think all of us do. We express things with terms and concepts that we're familiar with and we work with. And in today's era, it's all information based, right? And I think in many ways that's really good. There are many, many cases where viewing traditional problems across all sciences, viewing traditional problems from an information perspective is incredibly helpful. But I think in other cases, and this may be one of them, if people view information too literally, right, then
Yeah, I mean, people are mostly worried about is matter traveling faster than light in the discussions I have had, and that's not the case. And
yeah,
anything
I,
else travels faster than light. It's hard to say what relativity really forbids from. I mean, people just say as a slogan, nothing travels faster than light, but that's not enough to build physics on, right? You have to be very
well,
careful about what can and cannot travel faster than light, as it were, right?
I'm going to cause trouble by asking this, but do you
Go
think that
ahead.
this might be connected to the ER equals EPR conjecture?
I have to say, I have no clue about it. I never even read the paper. I have only slogan
Okay.
level access to it. Yeah, I'm afraid yeah, I'm just worrying about arrival times for last 5 years. I mean,
Well,
uh,
because the idea was, right, the basically what and this I if I remember right, they worked this in reverse, but this was Juan Maltasena and then
yeah,
I
I know
forgot
the
the
players,
yeah,
Lenny,
and
right?
yeah, so Leonard Susskind and Maldacena, and Susskind, if I remember right, they were looking at black holes and saying, you know what, this is the same thing as entanglement. And for me, the question I'm asking is, wait a minute, if it's an equals, is that a two-way street? Does that mean entanglement may use some form of wormhole? And if that's the case, even the entanglement wouldn't be traveling faster than light. So.
Yeah, I mean, I honestly have not much to say about that because I have to say the stuff that I was describing to you earlier is much more concrete, and that I'm very
Yeah,
sure
I
of.
know.
So, I mean, wormhole
Sorry.
solutions, I am not very sure of. I mean, never saw them in a lecture or in any reasonable stretch of what. So I'm actually just trying to balance myself within territory that's close to already working experiments, which already describes known experiments, and what's in the periphery, but not wildly out of scope. So, the reason I also focused on arrival time experiments is because it's in the vicinity of scattering experiments. So, asking for the arrival time of a particle is an aspect of scattering, and scattering is a holy grail of quantum mechanics. The best tests of this theory historically, starting from de Broglie's Nobel Prize for this Davison and Germer experiment were all scattering experiments. And it always, baffled me that the moment I learned about it from my mentor and teacher, Detlef Duer, that people don't ask about the arrival time of the particles in the same experiment. So that gives me even sort of grounding in possible real experiments to explore this type of stuff because if anything interesting happens here, then I have reasons to believe that it happens in our real world. So, yeah, and that ties to the point you made that this is really doable. This is very important.
Yeah,
And
and what surprised me is it surprised me that people are already testing this. So,
well, not really. I mean, that's a huge disappointment, to be
oh,
honest.
but I mean, they're testing arrival times, right? They are using arrival times for other
They're not
tests.
testing it, they're utilizing it to do something else.
Okay,
So
okay.
that's good and bad, right? I mean, on the one hand, this shows that you need to worry about arrival times because you're doing these experiments to measure arrival time for what? And the answer is to report some other quantities like momentum and energy. I mean, it's something obvious, right? You cannot stand in front of the particle and suddenly its momentum will drop at you. You have to do a sequence of steps, and lab stuff is very tricky. You have to do multiple steps, make various theoretical assumptions to convert quantities that you get in these different steps to get your final result. You know, what CERN calls the energy of a muon at the end of the day is a sequence of a lot of processing. But processing and conversion is theory dependent. So they presuppose some theory to convert, let's say, a measured arrival time, which is directly obtained, to a reported energy value. Now, quantum theory, as I was saying you, is as the textbook quantum theory is completely silent on what the arrival time is. And the confusion is further cemented by the availability of all these competing proposals, which actually make different predictions. Like literally, you don't even have to work hard to see it. So then one has the question here that when people are measuring all these arrival times and there is so much success in particle physics in what they do, how can they have that in the face of this glaring gap or issue about the quantity which they used to get what they wanted, but the very quantity has no clear theoretical meaning or a standing in the physics. So there is a practical side to it about the consistency of physics as it is done. Like the theory to experiment connection has lot of makes a lot of contact with arrival times.
Okay.
So,
Okay.
however this discussion proceeds, whether we have fantastical superluminal communication or not, at least physicists have to figure out arrival times because it is needed to, understand other things which they're already basing further theoretical development on. That's one thing.
Yeah.
The other thing is, as you said, they are able to measure arrival time. So this challenges the other view that I often hear in the literature is, oh, we cannot measure arrival time. It's not measurable. It's not an observable. And that goes back to, this is the typical rhetoric of inevitability of quantum mechanics, where they have a certain result following from linear algebra and about the structure of operators. And they say, this is not observable. But come on, there's a guy doing an experiment. Do whatever you want, but make a prediction for that experiment. I mean, that's the attitude I took. And historically, this you haven't heard a lot about this issue because of these kind of rhetoric that it's not an observable, it's not measurable, and that I have seen written in print that discouraged many physicists from walking along this path because some famous guy like Pauli said it's not observable and things like that. So so the point I was making is because people can measure these things, I go and tell the physicists, look, you cannot reply by saying you cannot face this issue with the slogan that it's not
Okay.
a
So
so,
it's worth pointing that out too. I should make a note. So
yeah.
s- physicists have said it's not observable, it's not
Yeah, and
measurable, but it is.
this goes back to a result of Wolfgang Pauli. My feeling is people like Jordan and others, this operator masters of the day, they surely had seen some version of it, but the official attribution is to Pauli, who published it in an encyclopedia article. Well, I mean, one can get into what led him to this conclusion, and if you
Mhm.
seriously think about it, it's a bit silly. And to use Pauli's terms, not even wrong, but that stuck on because he's a famous physicist, and that's a nice result, nevertheless. And by the time people appreciated it, they really got sort of arrested by it, and it stopped thinking in this direction. And at this point, it's no longer fashionable to say that because everybody knows that, as I was just explaining, people do time what are called time of flight measurements all the time. And there are whole like volumes written on time of flight momentum spectroscopy, time of flight, so and so. Chemists use it a lot to study aspects of chemical reaction. I mean, to give an example, you take a hydrogen chloride molecule, like a single molecule, put irradiated with laser light, it splits the chlorine and the hydrogen, and they measure the time of flight of the hydrogen, and they see very interesting pattern and peaks that gives information about certain aspects of the chemical reaction and so on.
Okay.
And then the question is, well, all this is quantum mechanics because you have nice interference patterns and stuff which you don't have otherwise. But there is not a clear quantum mechanical road to that because it passes through the territory of arrival time on which it has been silent famously or infamously from the beginning. So there is a lot of theoretical advance, like of a fundamental physics nature at stake here. And however, these experiments, I mean, as I said, I mean, signaling seems to be a robust undercurrent of the available proposals. I'm not suggesting that one couldn't do better. If somebody comes tomorrow and says, "Well, I have found a arrival time prediction, which is adequate, makes all the right predictions in the known territories, agrees with experiment, and is within the scheme of quantum mechanics." And I think many people are in that boat. I mean, that's an open challenge, I would say. But from the known proposals, as Will has shown, and as me and one of my colleagues, Sandro Donati, we have shown, the known proposals don't have that feature, and that's just easy to check. It's even an undergraduate student can do that with few
Okay.
weeks of work.
Well, Siddhant, thank you so much. This is no, this helped. In fact, one of the reasons I was asking dumb questions was when I go
No,
back through
no,
this,
it
then I
was
can use timestamps based on me asking dumb questions. So,
no, no, that's fine. I think all the questions I liked. It, I mean, I had something to say, so I at least I understood your questions.
um, the other thing I was going to ask, do you think that I could share this video with a couple of colleagues that I work with? If that would be okay? If it's okay, I don't want to, again, I'm trying to be very
I
sensitive to what you
mean,
feel comfortable with, but
I don't think I said anything, let's
okay.
say. Well, I mean, if you like, I should just make it clear that, of course, as always, these things are actively debated. There are eminent
Yeah. Yeah.
physicists who think this, they don't say that the calculations we have done is wrong, but they doubt the physical adequacy of the calculations. And this is now going on and on for a long time. So my, of course, personal opinion is they are trying to save the day by whatever they can, but it seems difficult. And at the end of the day, as I said, signaling or not, we do have to figure out arrival times, and
Yeah.
that the least we owe to physics.
Ultimately, it sounds like this line of inquiry is beneficial to physics, no matter what, no matter how you approach this line of inquiry, this line
A
of
lot
questioning.
of good physicists have contributed to this. I should make that also clear. And that's very nice. And because it hasn't been a very crowded field, unlike, let's say, ADS CFT, there's even a sense in which you can surround it and feel like you see how the field has developed over a period. There are not millions of papers coming out on archive every other day. So it's a excellent avenue for young physicists to work on because if you, I mean, now with tools like Mathematica and some other software, you can actually do a lot of these calculations, even if you're not, let's say, very good at analytical computations. And I do see a lot of newcomers always writing interesting papers, proposing new setups. As you know, Will is one of them. He always comes up with new setups every other day, so he's super active.
Yeah, that's exciting. That's exciting. Well, if it's okay, let me go for now. I have enough to work on
Sure.
questions for, and
Yeah.
let's definitely try and schedule a podcast. And the
Yeah.
Scientific American article, I have that as well. And I am
Yeah.
really excited because
Also, you
I
could look at Tim Maudlin's podcast with Sean Carroll. There, he has also
okay.
said a lot about this stuff. Maybe you have some questions answered there. It would be nice if you invite him as well. I think he can say more on causality and all that stuff because that's really his area.
Yeah.
He's the
Actually,
world of.
I'm going to do a I'm going to do a follow-up with him as well.
Ah, okay, that's the plan. Okay.
Yeah. Yeah. Again, the response that I've had, usually from physicists, when you hear crickets, it's they're dismissing an idea without seriously thinking about it. And so what I'm trying to do is reframe this in terms of, hey, loophole, right? And if they look at it from that perspective, and I think if they realize there's value to this experiment,
Mm.
regardless of what you're searching for, right? I think that could be enough to get people more engaged.
Maybe
So,
we should just start from the whole issue about arrival times and how such a practical thing is a mystery in quantum mechanics. And
yeah.
that leads to then signaling potentially. I mean, as of now, I think it should. Who knows?
Okay.
Well,
Well, let me do
okay.
that. Well, Siddhant, thank you again. Thank you so
Thanks
much.
so
And
much
you
for
have all
your
my
time.
contact info. I'll email you probably a little bit
Yeah,
later
sure.
today.
The next few days are slightly busy for me. I have to
Yeah,
say that in advance.
myself
But
also.
yeah, and yeah, as always, I'm sorry I reply late and
Oh,
it's
no, no, no problem at all. Siddhant, thank you so much.
thank
Thank you
you so
so
much.
much, sir.
Thank you. Bye. Have a nice day. Take care.